Hello, everybody. This video is to present the Advanced Energy Storage Program. And I'm Professor Hudson Zanin, work with University of Campinas and the School of Electrical Engineering. The main idea of the project is to present this video, actually, is to present this new project we have. Most of the guys probably don't know that is related to the electrification of the transports in Brazil. For us, the main idea is that we have electromotor, and then what we have behind that going to power is going to have must be a solution that we need to develop in this country. And the specific solution is that project where we use a fuel cell to convert ethanol in electricity. And then this electricity move electric motor. The truth is that this kind of system, the third generation of the fuel cells, are not fast enough to warm up. And then there's a need for a hybrid system where we have the battery and the supercapacitor powering the motor when they're warming up. And the main point here is that the solution is not going to be developing anywhere else but here. I'm going to tell more about this very soon. So the ACS, the Advanced Energy Storage Division, start with Shell and FAPESP in the Center for Innovation on New Energies, and we are one of the divisions. But we are becoming a program now. Beyond this project specific, we are becoming a program with lots of projects inside. So we start with this one where we produce lithium oxygen batteries in the TL technology ready level 3, and supercapacitor when we are moving now to TRL 6, where we develop from the coin cell. Actually we start from the material science, and then we produce ink, and then coin cell, and then pound cells, just like we are showing here. I'm going to share more detail very soon. In this new project, we are having the production of this solid oxide fuel cell, which is the third generation of the solid oxide fuel cell. The films are thin. You can use metal as interconnect. The sealing is much cheaper, and the cell can warm up very quickly, up to 6 degrees, 600 degrees, where the cell works. And that's much better for application right now. So the industry is very excited with this. So these projects are going to develop this, and also two types of battery that we are not doing right now intensively in this initial project, which is lithium ion and lithium sulfur. The last one is related to the is more focused on energy density, and the other one is more related to power, especially when you work with a nickel in the electrode material. The third project here that is integrating this program is a FAPESP initiative related to a young investigator. Is 3 million reals, and there's a Shell, Toyota, AVL, and SAI, and other companies as well here supporting this idea. Is that the idea is to move from this initial pound cell to modules, but also produce cylindrical cell, because the automakers really prefer this type of cells. Pound cell is very good because it's easier to make, is important to tools, but the cylindrical cell are preferable for some automakers, some, not all of them. And we are going to produce the cells and the models. And also in this project, we're going to produce a redox flow battery, which is a very specific type of battery for a stationary solution. What I have said so far is very good for mobility, but now we are also have some initiatives to a stationary solution, energy storage stationary solution. I'm going to say some more detail about this later on. And this four project is related to the conversion of ethanol in a fuel in the fuel cell. That's very important to produce that in the way that we do not contaminate the cell, and that's we're going to do that. There's some brands and companies that's going to support us in this project. What we have so far is that we produce material science, we produce coin cells, and then we produce pound cells for sodium ion, supercapacitors, some types of battery, but it's very preliminary data. And then we focus on supercapacitor and lithium oxygen battery here in this project. This is an initial project. Hopefully, if we have enough time, we're going to put this bonus activity, which is producing a modules of pound cells with the system, the pound cells we have here. But if not, this new capacity project, Young Investigator, we plan to produce these models of pound cells from the pound cells, also produce, prepare a lab scale manufacturing to produce the cylindrical cells and then the models. Also, we are going to move from the benchtop initiatives we have here from redox flow batteries. This kind of system is the size of our hand, so it's a massive system compared to coin cell, for example. But we are going to extrapolate this system in this first project. It is FAPESP, it is a 5 years project, the Young Investigator, on this topic, and we're going to move to container level device, where we plan to play with different association of electrodes, where more electrode we have more power on the system, and more electrolytes or less electrolytes, we have more or less energy. So we can disassociate power from energy in this kind of system, and this could be very big. This solution is appropriate where the energy density doesn't matter. So, for example, in a building, you can have a cheaper way to store the energy by using this kind of system. And one very expensive part of the system is the electrolyte, where the energy is stored, and the vanadium is the most used one. And we plan to replace this one by applying some salts. We have a lot here in Brazil, like iron, chromium, cerium, zinc, and different types of replacement of the vanadium. So this project about electrification of the transport, the main pillar is the fuel cell. So to produce this fuel cell, that could you use ethanol, which this molecule here would have 6 hydrogen, oxygen, and carbon. In electricity, we need to do 2 steps. One is convert ethanol and CO and hydrogen. So because inside the cell, these guys are fuel, and this fuel could be converted with oxygen ion in water and the CO. Okay, and we remove electricity. This electricity power the electric engine. Okay, but also power the battery. So if we use this kind of technology, we can fulfill the tank. We can fill the tank with ethanol, bioethanol. In this country, we have a lot, and then we can electrify the transport with that. So that's a clever way to reduce immensely the cost of infrastructure on this country and have CO2 neutrality, because when you continue to have CO2 on the car and the gas outlet, but the plant in the field collect the CO from the atmosphere, CO2 from the atmosphere, and combine with the sunlight to make a photosynthesis and capture the CO2. So there's a cycle where the CO2 is neutral. And this country is so big here, and there is no way that we compete the production of ethanol with the food, as people used to say. That's completely wrong, the misconception about this country. So in order to this fuel cell to work properly, we need to use a metal as a interconnect. And that's a cheap way to use interconnect, because this last generation used ceramic and all this other types of interconnect, because of the temperature used to be higher than 1,000 degrees. Now the system working 600 degrees, and that's work for this conversion, and this is the temperature necessary for this conversion. And this optimum temperature there's issues with this temperature, because inside the cell we have a lot of ceramics, and the conductivity of the ceramics is affected by this low temperature. And the way to solve this the problem is to reduce the thickness of the film and make it thinner films. And these thinner films allow the ion conductivity inside this membranes. So what we're going to do is we're going to use this metal oxide, this metallic interconnect, put some diffusion barrier layer to avoid a diffusion of the iron, and to avoid chromium and nickel to contaminate everything around, and also avoid the migration of the nickel inside the anode to the interconnect. So we are expert on producing this by tap casting, and also by several techniques, CVD, PVD, which is a chemical and physical vapor deposition, and also electro spray. That's all this facility we have here, and we already produce this kind of system. Also, the main catalyst for carbon is nickel, and this nickel here is an issue here, because we have what we call a cock formation. There's a thin layer of carbon forming, and that reduce the power of the system. And we have some strategies to avoid this, like replace nickel or part of the nickel by copper, or make an alloy of this, and also use some niobium and other types of metal. It's possible. We're going to use in this last project we show. We're going to be focused on the solid oxide fuel cell, especially on the reforming of ethanol, because if we can use this interconnect, if we can print this in a 3D print, just like this STM image and this image here, where we printed that already. And then we have a proper catalyst like we're showing here. We can convert the ethanol and hydrogen and CO, and that's going to be the fuel, and that's going inside the cell, and that's avoid the contamination. And that's kind of system that could be recycling, and then when this for somehow the cell stop working, we can do a refreshing. We already have done some of this research already here at Unicamp. And at the end of the day, what we want is that to have the system with a packing, where we associate all of this solid oxide fuel cell together, but also integrating the reform inside the cell. That's the one very important task. So what we said here is that advanced energy storage is going to be the program with a production of models of different types of battery, sodium ion, potassium, lithium, and supercapacitor as well. We also going to be to produce a solution to container level redox flow battery. That's the first time in Brazil. And then the reformer as well. So we're going to produce a solid oxide fuel cell with reformer integrating it. Almost all of this technology were not produced in Brazil in the past, and we are assuming the whole of in doing this with excellence. So hopefully you guys enjoy the video. If you have any contact and idea, please do not hesitate in contact me. Okay? Thank you for watching.